This is video 4 in a series of reviews designed to help you prepare for the unit exam on interactions. This video is on population growth. For a long time in class, we've been focusing on how the actions of populations affect other populations. We've been focusing on the interactions between populations, the effects on community. And so now we talk about population growth. We're going to talk about different reproductive strategies and how they impact the size of the population, but also how they impact the growth rate. And I think as we talk about it, you'll be able to see how certain features of the strategy impact the other organisms who are living in the environment. So we began with the discussion of R strategists, those organisms who are typically small and part of the prey trophic level or trophic levels. And so they have a short lifespan, not only because they're prey, but just because that's just their lifespan. That's what nature intended. So they develop very early, and they will reproduce at an early age. And typically, but not always, they only get one shot to reproduce. So they produce lots and lots of offspring because they're not going to provide any care. This is about quantity, not quality. And they, somehow they're aware that a lot of those babies or eggs or whatever it is will be consumed by predators. So again, they are not, focusing on their reproductive energy on one or a few. They are splitting their reproductive energy between many offspring. And so that means, each individual is getting very little free energy for themselves. And that's in contrast to our K strategist, who has one or a few offspring at a time, and they spend a great deal of their free energy rearing that offspring, protecting it, and so on. This is more a quality effort versus quantity over here. So again, we said as a prey individual, the environment will be unstable, much like the stages of early succession will be unstable. And so what we see in our strategists is a J-shaped curve that illustrates their population growth. It is slow growth that suddenly, results in a very large population. And so remember that the R strategist is geared towards maximum reproductive rate. So obviously, as we're talking about our strategists, insects and rabbits, bacteria, rodents, and weeds, we can see that some of their interactions are going to affect other organisms. Like, for instance, insects can be a real problem for the crops that we grow. They can become an issue. They can eat up all the crops. They can invade your homes. Termites could basically strip your house down, by eating the wood. So those are some of the interactions here. These oftentimes will become pests because they reproduce so many so fast. On the other hand, our K strategists are going to be larger organisms, again, like elephants and birds and primates like ourselves, lions and horses, larger organisms who are typically the predators in the ecosystem. So their environment's going to be stable. They're going to have plenty of energy in most cases to survive, and they're going to have a long lifespan. So their development takes place over many years, and so, as such, they reproduce at a later age than our R strategist. And having a longer lifespan means they can reproduce typically more than once. So when we look at their growth curve, it's logistic, not exponential. Exponential is that J-shaped curve, very rapid reproduction. Exponential is slow and steady that reaches a plateau or a stable equilibrium phase. And so our K strategist is geared towards reaching K and staying there, reaching the maximum capacity for that organism in the ecosystem, right? K is the carrying capacity, the maximum number of individuals that an environment can support. And like I mentioned, this idea of a perfect flat line where death rate equals birth rate, that is zero growth, that's ideal. That's in theory. Real populations kind of fluctuate around this value. So obviously, as predators with long lifespans, these types of organisms will, affect other organisms in other ways. They'll have nests that they need to guard, and those nests might be in a tree, or there'll just be many different kinds of interactions that result from this kind of lifestyle. We next looked at the phases of the logistic growth curve. And this is something that you definitely do need to know on the unit exam, for the unit exam. I'm telling you, there is at least one question on this. So make sure you know the different phases. Lag phase, a period of slow growth. You know that. It's still a positive slope, but, it's not extreme. Then we have a phase of very rapid exponential growth, followed by deceleration or a slowdown in growth. And finally, this stable equilibrium phase where the growth rate is 0, birth rate equals death rate, and the organisms are hovering around K, or carrying capacity. So the next thing that we did was we calculated rate from a graph, and we said, be careful when you use rate. Typically, it's going to refer to the amount of product or the number of products that you make in a particular time frame. We're using the slope formula, rise over run, delta y over delta x, but we've clarified right here by spelling out what the delta y means and what the delta x means. It's the difference between the two y values, or the change in the two y values, and the change in the two x values. So as a class, I asked you to calculate the mean rate. That is, what is the average rate? A lot of us were not sure what mean meant. And just remember when we talked about qualitative versus quantitative, biologists don't talk about qualitative stuff like if someone is mean or a predator is mean. Mean is a qualitative term. For us in biology, mean is a quantitative term. It is the average. So I'm asking you for the mean rate. What is the average rate for the duration of the experiment? And so we said, when you hear that, that means that you're going to be using the whole line, and your y2 will be the end point, and your y1 will be the beginning point. And then of course, we're talking about y values, right? We're looking at the end point here and the beginning point here. I think that was something that people misunderstood. The y values, you've got to look up here to see at what time that is, and then you go across to get that value, which we are estimating 675, 680, something like that. And we had also said 0 in the morning classes, but some astute individual pointed out that how could you start off with 0 in a population of yeast? So we went ahead and adjusted that to 1 in later classes. So again, our y2 was the ending population of about 675 or 680, and our beginning population number was about 1. Then we looked at the x values. The final x value is 18, and the initial is 0 times 0. And so what we ended up with was something like 675 or 680 minus 1, and 18 minus 0. And then, of course, when you do the math, there's a range, 37 to 38 cells per hour. So later in the day, I had time to do more practice with a different class. And so we practiced calculating the rate between 6 and 10 hours. And so the students had to go to 10 and find out about how many individuals there were at 10 hours. And that's approximately 500. And then at 6 hours, it was approximately maybe 175, probably not 200, but 175. And so that was our numerator, 500 minus about 175. And then our denominator was very easy. The end time, which was 10, minus the start time of 6. 10 minus 6 is 4. And so when we calculated it, we got the particular answer, which I don't remember offhand. But like Mr. Anderson, I'll tell you, you can do the math by yourself. That was 500 minus about 175 divided by 4. And with this, I'm going to close. You can hear that my voice is ragged. It's been a long week, and so I need to rest my voice. I'll finish up the rest of the videos and post them next week before the test. So have a good weekend, and see you Monday.